In this video, we're going to provide a brief review of probabilities with emphasis on the maximum likelihood distribution. So assume here that we have an example in which 20 people have answered a multiple choice question, and we have recorded the amount of time it takes for each of these people to answer this multiple choice question. These are the results of our recordings. So we see that for most people, it takes around 9.5 seconds to answer this question. However, there are some people for whom it takes a little bit shorter, and for some people for whom it takes a little bit longer. Now, the question is, what do we observe and whether we can fit a probabilistic distribution in this data? So we observe, because most of the values of this data is centered around a specific point, and some of the values are scattered to the left and to the right, we observe that a possible distribution from which this data could have been generated is the Gaussian distribution. There are multiple examples of Gaussian distributions that could fit this data. And we have to say here that the Gaussian distribution can be thought actually has two parameters, has this bell-shaped curve, and has two parameters which correspond to the mean and the variance sigma square of the data, of the distribution. So we can see an example of Gaussian distributions that are centered around zero, and we refer to these as normal distributions. And these blue, green, and yellow lines have a mean which is equal to zero, but have different variance. On the contrast, this green line here has a mean equal to -2 and a variance of approximately 0.5. So these parameters are basically the two parameters that characterize the Gaussian distribution, and are usually parameters that we have to estimate from our data. Now, if we go back to the example of the multiple choice question, we can try to see whether we can try essentially to eyeball the data and try several of these Gaussian distributions. So for example, here we can try a Gaussian distribution with mean 10 and variance at 2.25, which would be this Gaussian distribution represented with this blue line. And we can try multiple other examples of Gaussian distributions. However, one wonders here if there's a systematic way to actually find the exact mean and variance of the Gaussian distribution that actually best fits the data. And actually, there is a systematic way to do that, and this systematic way is called maximum likelihood estimation. So instead of trying various parameters mu and sigma square that fit the data, we are going to assume that this mu and sigma square are unknown variables in an optimization problem, and these unknown variables are going to be found from our actual data. So assuming that our data are represented by samples x1 through xn, from the definition of the normal distribution, and also assuming that our data follows a normal distribution with mu and with mean mu and variance sigma square, we know that the probability of observing sample xn, for which we know its value, is equal to this expression. And this is the expression of the normal distribution, of the Gaussian distribution, nothing else than that. This sample xn, this value xn, is actually a known value. So this xn is being represented by one of these blue values here in this multiple choice question example. Now, if we were to find the joint distribution of all our data, then assuming that our data actually is being generated by the same distribution, which means that it is identically distributed, and assuming also that our samples are being recorded independently from each other, then the joint distribution of all our data can be the product of each of the probability of each of our samples, x1 through xn. This product can be, when we substitute the definition of our Gaussian distribution of mean mu and sigma square, can be actually represented by this equation here. So a reminder that in this equation, all our samples x1 through xn are actually known, and the only unknown variables are the mu and variance sigma square. And therefore, what it makes sense to actually do now is to maximize our joint distribution and essentially found the mean and variance that maximize this joint distribution. And if we do those calculations, so if we compute the first order derivative of this distribution with respect to mu and the first order derivative of this distribution with respect to sigma square, and we set each of the two to 0, we are going to actually find that the maximum likelihood estimation of the mean of the Gaussian distribution is equal to the sample mean, meaning the average of the values of all our samples. And the maximum likelihood estimation of the variance of the Gaussian distribution is equal to the sample variance. Basically, if we take the variance of all our samples, x1 through xn. So the general way to describe the maximum likelihood estimation, assuming that we have a set of independent and identically distributed samples, and assuming that all our samples are drawn from the same distribution with parameters theta, this distribution can be a Gaussian distribution, but can be any other type of distribution with any other set of parameters theta. We want to find these parameters theta that maximize the likelihood of our data. Since our data are independent, the likelihood of all our data is equal to the product of each of the separate likelihoods for each data sample. And what we need to do following that, after we have computed the likelihood, is to find the parameters of the distribution theta that maximize this likelihood lambda. In practice, sometimes, instead of maximizing the actual likelihood, we take the logarithm of the likelihood and we maximize what we call the log likelihood of our data. This is equivalent in mathematical terms because the logarithm is an increasing function. And it also provides computational advantages, especially here if you think about it, since we have to do with values, with probability values. These probability values are usually between 0 and 1. Therefore, if we take the product of several values that are between 0 and 1, this product will result in being very small. So by taking the likelihood, essentially we can get a better resolution for our problem. Now, another distribution that is of interest in the case of logistic regression is the Bernoulli distribution. So the Bernoulli distribution represents the process of tossing a coin, or else represents the process of modeling a binary outcome. If we have a binary classification problem, it can be the process of either having class 1 or class 0 as an outcome based on our data. So essentially Y represents the outcome of a single trial, which means if we have a single sample, what is the probability of this sample to belonging to class 1, and what is the probability of this sample belonging to class 0. Equivalently, if we just toss a coin once, the Bernoulli distribution represents the probability of this toss to result in heads and the probability of this coin toss to result in tails. So this can be mathematically expressed with this expression here. And this expression is the probability of our outcome given our parameter of the Bernoulli distribution theta. This parameter theta represents the probability of having outcome 1 as a result of the single experiment. If we had a fair coin, this theta would be 0.5. If we had an unfair coin, this theta would be as a number between 0 and 1, but of course not 0.5. So now the probability of observing an outcome y given our parameter theta is theta if our outcome is actually 1 and 1 minus theta if our outcome is 0. Now, instead of having this complex expression here that mathematically will be difficult to handle, we can summarize this expression as is being reflected here. So essentially, when y equals 1, the result of this will be theta. When y equals 0, the result of this will be 1 minus theta. We can also derive the maximum likelihood estimate of a Bernoulli distribution in the case where we have multiple samples. So assuming here that we have a set of samples, x1 until xn, and these are samples that correspond to n different outcomes of a Bernoulli distribution. So in this case, it means that we have let's say we have tossed a coin n different times. Each of these times we had found either an outcome 0 or an outcome 1, head or tails in the case of the coin. And we want to find what is the parameter theta of this coin toss. So what is the probability of our outcome being equal to 1? We know by the definition of the Bernoulli distribution that the probability of a single outcome is equal to this expression. Therefore, what we need to do based on what we discussed about maximum likelihood estimation is we need to find the joint probability of all our samples, which can be represented by the product of each of these separate probabilities. Now, because it's difficult for us to handle these multiplications, what we can do is we can actually compute the logarithm of this joint probability, which is being referred to as the log likelihood. If we apply a logarithm in this above expression, and we actually solve a little bit, describe analytically this expression, we are going to find this final expression here. What we have done here is that we have taken advantage of the property of the logarithms. So the logarithm of a product is equal to the sum of the logarithms. And also the logarithm of theta raised to the power of xn is equal to xn multiplied by logarithm of theta. These are just logarithmic properties here. So after that, we would like to maximize the above expression with respect to theta. Therefore, we want to find the first order derivative of this log likelihood with respect to theta and set this equal to 0. If we do the calculations, by taking into account that the first order derivative of logarithm of theta is equal to 1 over theta, and similarly, the first order derivative of this expression is equal to minus 1 over 1 minus theta. These sums here do not depend on our unknown variable. These sums are just numbers. Essentially, each xn is either 0 or 1. So after we compute this first order derivative and set it equal to 0, we are going to find, when we solve for theta, that the maximum likelihood estimate of the parameter of the Bernoulli distribution theta is equal to the average of our outcomes. So essentially what this means is that if we have a set of n independent trials, and we have assumed that 6 out of these 10 trials have an outcome theta, then this maximum likelihood estimation of our parameter theta will be 6 out of 10. And by performing the second order derivative test, we can actually observe that this is a maximum. This estimate corresponds to a maximum. Now let's go a little bit back to our slides. And what we would like to also demonstrate here is that beyond the Bernoulli distribution, which corresponds to a single binary experiment, we can also have the binomial distribution, which corresponds to a binary experiment, but this binary experiment is conducted not over a single trial, but over n independent trials. This formula here is the definition of the probability of the number of times that we can get an outcome equal to y, where y is equal is either 1 or is 1 or is 0 over n, over the n different independent trials that we have run our experiment. And here are some examples of our binomial distribution. So we can see here, for example, in this blue line here, in this case, we have run our experiment 20 times. And in this specific distribution, our parameter theta is equal to 0.5. So it means that for each of these 20 times, with 0.5 probability, we get an outcome equal to 0, and with 0.5 probability, we get an outcome equal to 1. So what we observe here, because essentially we have a fair coin that we toss 20 times, the likelihood of our coin yielding our positive outcome 10 times is the highest, because it is a fair coin and we toss it 20 times. However, if we have an unfair coin, as it is being depicted in this green line here, and this unfair coin is more biased towards the positive outcome, because the parameter theta is equal to 0.7, then this means that the probability of observing a positive outcome is going to be the highest if of observing a positive outcome more than 10 times is going to be higher. Just because if you think that we run 20 trials, and if we are biased towards the positive outcome, then we are going to observe this positive outcome more times than 10. Similarly, instead of beyond the binomial distribution, instead of having a binary outcome, we can have k possible outcomes over our n independent trials. And this is what we call a multinomial distribution. So the outcome of the multinomial distribution now has k different variables, and these k different variables represent the number of times each outcome k will get selected. The parameters of this multimodal distribution are the probability of observing each of these k outcomes, and these probabilities are represented by variables theta 1 through theta k. The sum of these probabilities equals to 1. And another parameter here is the number of our independent trials. You can assume that a multinomial distribution is the example of tossing a dice and different times. If a dice is fair, then each of these parameters will be 1 over 6, because we have 6 different outcomes. Each of these will be equally likely. If the dice is not fair, then some of these parameters, theta 1 through theta k, will have values greater than 1 over 6, and some will have values less than 1 over 6. So this final expression here represents the probability of seeing each of our k outcomes y times, where y ranges from y1 through yk. What this means in practice here is that if we have n independent trials, the sum of these observations will be equal to n, and the probability of observing each of these combinations of outcomes, which is represented by the vector y, is proportional to the probability of the first outcome times the number of times the first outcome was observed, the probability of the second outcome multiplied by the number of times the second outcome was observed, and so forth and so on. So this multinomial distribution will be particularly important when we talk about the multi-class logistic regression. And the reason for that is that when we model the problem of the multi-class logistic regression, we are going to have k different classes, which correspond to the k possible outcomes. And we're going to have n independent trials, which are going to be our n training samples.